thrilled to have Sabrina telling us about lifting swing surfaces to AdS, and we hope that she'll follow up this virtual talk with a physical visit to TIFR very soon. Over to you, Sabrina.
Thank you for having me. Yeah, I've never been to India, so that'd be super cool. So basically, this talk is about work in progress with Robert Myers and Jackie Caminati, who's a grad student. And I've had a lot of fun computing various things with it, but it's still very much a work in progress. And so I guess for this slide deck, I'm kind of leaning towards a couple themes of what we were finding. But I'm happy to make it interactive and try to workshop maybe the bigger punchlines. And also, if I don't have enough details, I will jump to an overleaf if I need to. So the outline of the talk is as follows. I want to have kind of three parts. The first part will be some context for flat holography. Some of you know, or probably I'm mostly a celestial holography person. Today, it's not going to be super celestial, which will be fun. And then in the second part, it's going to be introducing a proposal for an entanglement entropy and a holographic interpretation of that for flat holography by Brumiller and friends, and then Wei Song and friends as far as the holographic interpretation called the swing proposal. And then in part three, we're going to try to see how we uplift that story to AdS. And then kind of it points to some questions in what is the status of an entanglement entropy in flat space-time? And so, yeah, basically, when you kind of go through the literature and find various proposals for Ryo Takanagi in flat space, you see that things that are not quite what you expect might have some interesting questions when we try to lift it back to what is the flat limit of the theory that we're taking. So first part of the talk, context for flat holography. I think this probably, depending on the audience, is basic review or not. Basically, we want to study quantum gravity, and an easy way to do that, as far as someone coming from a string theory academic background, is we get to cheat and try to find some dual description that's lower dimensional and doesn't have gravity. And that could be motivated by talking about quantum field theory on curved spacetimes and Hawking pair production and whatnot, black hole area law instead of it being extensive. Or you can have explicit top-down constructions where we know what the dual is, and we have a lot of fun with that. Now, the confines of AdS CFT might not be as relevant to the kind of space-times that we're probing. So one thing nice about the framework, if we try to figure out how to find a dual for asymptotically flat spacetimes, is that the mathematics of asymptotically flat spacetimes should approximate a broad range of physics. And this can be from amplitudes and collider experiments up to gravitational wave observations. And so a lot of my early work in grad school is on some symmetries that would be there for a theory that's semi-classically, I guess, just gravity, but in S matrix insertions, you get soft theorems and you have some memory effects associated with them. And those are things you try to measure with LIGO or LISA. So it's fun to think that if we could build a holographic description of asymptotically flat spacetimes, we'd be covering a long range of physics, even if technically lambda might not be zero in real life. So when it comes to talking about holography, and especially flat space holography, because I guess that's the subfield that I know more about, there've really been two different approaches. And I would say that for the flat holography program, it's a lot of bottom-up work, especially in celestial, where we're basically saying people have studied for years the asymptotic symmetries of asymptotically flat spacetimes. And then the kind of push that ends up being kind of the motivation of, say, celestial holography is all about the fact that that symmetry structure is richer. And so what are you going to do with all those symmetries? And asking those questions lead to these ward identities, soft theorems, et cetera. So it's really starting from the fact that we should match symmetries on both sides. I think that there is starting to be some more steps towards, at least there's questions in celestial holography about things being unitary because the spectrum in the Lorentz boost basis looks weird. But ideally, we would be able to be like an amplitudes person and talk about what consistency conditions of this object, which is the scattering amplitude, have. And then various reasonable expectations, like we have a bulk graviton, so that implies some symmetry generators in the dual, et cetera. So most of celestial has been bottom up, and I would defend the fact that, like, even if you're playing with symmetries, if there's a larger set of symmetries and you know how to deal with the kinematics, then you can isolate out that from the dynamics, so that's fun. But the kind of fun thing about celestials, we recently had some sort of top-down construction too, coming from Kevin and friends. But generally, top-down approaches are like, you know, both sides of the dual, and you know what limit you're taking to have this AdS CFT construction. And it turns out there's ways to have a twisted holography construction where you have a flat space-time and the twistor space of that flat space-time appearing from some kind of consistent truncation of AdS CFT. So the gold standard would be top-down. Most of what I'll be talking about in this talk is bottom-up. And in the context of flat holography, but both approaches could exist, I guess, in either thing.
So Sabrina, this top-down approach that you talk about, due to Kevin, you said, is that is it really the flat space or asymptotically flat? Because I remember translational symmetry was broken because the
space
had something in the middle. So are you talking about that or something else?
I'm just referring to that paper. So it's the twister space of Burn space, and I guess Burn space isn't even the right signature either. So it's the wrong signature. And there is some, I guess, I don't know if you would call it a defect or whatnot. The geometry isn't quite just flat space, but it's an asymptotically flat space, at least close enough. So yeah, so basically there it was kind of fun because you're really pushing too far. I think that this 2D CFT framework and all the symmetries you might extract from collinear limits of scattering that way. And then asking, can I have a duality where the CFT dual has these features? And then the chiral algebras of Kevin and friends were exactly that structure. And so they understood it that way.
Okay.
But, yeah.
Thank you.
Yeah. Okay. And so with this new Simon's collaboration that we have, what I find fun is that there are a lot of subfields of Hep theory that care about flat holography, not just the celestial group. And sometimes it's more or less explicit. For example, most of the people who do it from qubit do want to understand holography in the real world. It's not like they're trying to stay in AdS. And I guess the Bootstrap program, a lot of S matrix insights come from there, and the S matrix itself, I would say, it's a flat space quantity. We're always flat space. So we all care. And in this talk, I'm going to try to delve a little bit into the if from qubit side of questions that they're interested in, and explore with my buddies here, Rob and Jackie, about some fun literature about flat space holography, entanglement entropies that I guess I didn't actually know about too much. And so just constructing a little lit map for fun, even though this is by hand, so it's not reasonable data science or anything. There's kind of a lineage of people studying, I guess, BFSS and Polchinski, talking about looking at a book point, at least the early versions of that, for extracting scattering matrix elements from holography. And De Boer and Solodukin in 2003 were looking at foliating asymptotically flat space-time or flat space-time, with hyperboloids where you could apply AdS CFT to each leaf. And a lot of the celestial story in Andy's IR business kind of was inspired by De Boer, and I guess a lot of the specifically 2D current constructions can be written nicely in terms of foliations, and I think Chung wrote that out more explicitly. But there's a whole other branch of people who've also been interested in flat space versions of holographic quantities that are of importance. And for this talk, I'm going to be focusing on some results that I guess I didn't appreciate as much just in my very naive little bubble of celestial and flat, which is this entanglement entropy computations by Grumiller, Bagchi, Riegler, and collaborators, as well as this holographic proposal for what the bulk dual would be by Jiang and Weisong and friends. So they're recent enough in that timeline, but they're a bit disconnected, and we're trying to tie it back in. So what's special about flat space? Well, I guess what's nice about AdS CFT is we have kind of time evolution in the bulk and on the boundary. Nothing so confusing about that. I mean, the fact that you have an extra bulk dimension is kind of the fun thing with holography, but otherwise we can evolve in time in the bulk. And the fact that the charges would be codimension 2 is a great thing for us, because then they're codimension 1 in the boundary theory. And I can talk about a dynamical theory living in the boundary that's dual. Flat space gets funny because of various aspects. So for me, I'm mostly interested in, or at least have been, in the radiative data. So any massless fields that are going to fly through my space-time, I want to be coming in from square minus and going out to square plus. And then I need to tie together where all of the other massive particles are going to enter and leave the space-time at past and future time like infinity. And any notion of conserved charges, I need to be matching across spatial infinity. And there's some subtlety with the fact that like the points, I don't know if you can see my cursor. Hopefully you can.
We can.
Good, yay. The points like here and here are really an infinite amount of time apart because of the order of limits. And so that causes some fun business with antipodal matching and all these like charge conservation laws. But in practice, I guess the one weird thing is if I'm talking about a theory that's supposed to live on this conformal boundary, I have to deal with the fact that this is going to be a null time direction. And I also expect some radiation or whatnot to flux through my boundary. And so what things are conserved is a little bit different. Yeah. So then the game that people play is you start with this class of metrics that are these asymptotically flat spacetimes. And in a good gauge where you at least kind of have tried to just isolate out some nice coordinates, you identify the physical fall-offs. You don't want to kill off radiation. And then you ask what diffeomorphisms preserve those fall-offs. And you end up with BMS instead of Poincare. And so that's the kind of fun thing about flat holography. And at some point, we're going to need to really deal with that. And from the point of view of if you're in 4D or whatnot, there's all the soft physics that comes out of it, because when you're doing a BMS transformation that's not in Poincare, you're going to be spontaneously breaking the vacuum, and you're going to have like extra soft graviton insertions that are doing that for you. Now I'm going to go on two little rants. I just called them rants. I think this is part of a talk here, so it's more informal. Basically, there are two kind of competing descriptions, not necessarily competing, for like what is the natural way to talk about this like flat dual. And so we really want a theory that's like living on the conformal boundary rather than just being able to understand holography and AdS and extract some flat physics in the bulk in terms of some part of the theory on the boundary. We really want a theory on the boundary to be dual to that flat physics. And so at least just staring at the Penrose diagram, the closest thing to being a codimension one boundary component that seems nice would be, let's say, null infinity. I mean, you can blow up spatial infinity, and maybe you can argue that that is better. And the Carolian description is thinking about a CFT that's living on that null surface. And you can ask questions about like what word identities would look like in that Carolian CFT, what correlators would look like, etc. And things go a bit weird because you're on this null hyperplane. Now, celestial is cheating a bit by basically smearing along the null direction with some kernel, so you're in a boost eigenstate. And from the point of view of null infinity, that's just a change of basis. You lose a little bit of the notion of things that should be like local on null infinity are now, you're smearing along that null direction. Things look like it's a 2D Euclidean CFT. It's no longer going to be, like unitarity in 4D wouldn't be the same like relationship to the representations of that 2D conformal algebra that you would expect if I was talking about a 2D Euclidean CFT that I'm going to Wick rotate to a Lorentzian one. So there's some subtleties there, confusions there about just saying it's a standard 2D CFT. But the one nice thing that celestial would do is if I was talking about massive states, I can kind of like bulk to boundary propagate an on-shell massive momentum to the boundary just as readily as I can do this smearing along null infinity. And so I'm not piecing together different manifolds. I always have a celestial sphere and it just has like different labels for the masses. But that won't be as important for the stuff I want to talk about today. And so for today's talk, Carolian will win. And the Carolian picture wins because if I'm in AdS and I think about a bulk point configuration, which means that I am thinking about some tiny little region in the center of my AdS spacetime that I want to think of as the flat spacetime where things are going to be colliding. And then I want to send things in from the boundary. I will have these two little windows that are kind of parametrically small. So the times are going to be pi over 2 plus or minus pi over 2 plus retarded time u over L will describe how this little window maps to my null infinity. And so I have a picture where I have regions of the boundary in AdS mapping to regions of my boundary in flat. And that's why it's kind of nice, because basically now I can think of things where I'm anchoring, say, my RT surface to some intervals here as being, or hopefully being analogous to asking about entanglement entropies here, but we're going to find that's a little bit subtle. And the second, yes, please ask questions because I go fast.
The left-hand side of your diagram is basically the bulk point setup, at least the geometry of the bulk.
Exactly. Okay. So left-hand side is both points up.
Yeah, one quick question. So what is this entanglement entropy supposed to compute on the dual side, like the putative dual side? Like in the celestial description, is it like oh, I guess you're not in the celestial description.
I'm not going to be doing celestial. Okay. I'm going to be cheating and not doing celestial. Yeah.
Okay. So it's like a codimension one slice, some kind of Cauchy slice of null infinity, and then you're looking at some spatial subregion of that. Is that?
Yeah. So I think that's the one thing about null infinity is you can look at things both ways. And so Rob had another paper with Anna and with Vincent where they were kind of viewing null infinity as the limit of a Cauchy slice, in which case you might want to talk about entanglement between, say, the future part of null infinity and the past part. And then you could artificially at least get a page curve, kind of like what Subrat Raju and friends were doing. And for the scope of this talk, we're kind of going back to maybe what would be the natural thing from the left-hand picture here, where I think of a time slice as literally just some circle here, which is also some circle here. And then I'm taking some interval on null infinity, which will have like a value of u and phi, say I've been 3D, delta u, delta phi. And I want to talk about entanglement entropy in a field, like a BMS field theory living on null infinity. So,
got it.
Yeah.
Thank you.
Good. And so another rant is about 3D versus 4D. Until maybe 8-9 months ago, I was totally a 4D person. I could say that's because we live in 3+1 dimensions. Yay, that's awesome. And then also the reason why mostly was because we're interested in soft physics. And so in particular, soft theorems, like the radiative degrees of freedom going soft, rather than just, I guess, like boundary modes. So I was totally convinced 4D is where you need to be to see a lot of the stuff that Andy's done, because you wouldn't have soft theorems, for at least for gravitational stuff and fun stuff like in lower D. But then I opened my eyes to 3D. Everything's just easier. You have the BMS algebra coming from Vera Soro. You have non-zero central charges. People have proposed entanglement entropies. People have proposed like bulk duals equal to them. 3D is nice. So I'm a convert a little bit for some things. So we're going to stick to 3D. Yay. Okay. So that's part one of the talk. How am I doing in time? Good. Okay. Now I'm going to try to introduce work from this 2015 and 2017 papers about the swing proposal hanging around for like a entanglement entropy, holographic entanglement entropy in flat space time. So AdS CFT, I think one of the core tenets a lot of people have really gotten a lot out of is somewhat of a bottom-up approach, in the sense that it's a pretty general principle that you want to equate geometry to entanglement. And in particular, you're computing this entanglement entropy, where if in my boundary CFT, I take some region A as complement B, I trace over the degrees of freedom in B, and then I compute this von Neumann entropy. That entanglement entropy can be computed in the book via looking at the area of a minimal surface. So that's nice that you have this proposal where you have a geometric quantity equal to some information theoretic quantity on the boundary. And this bulk dimension is kind of geometrizing that notion of entanglement between the regions A and B. You have to deal with the fact that you have divergences here. So both quantities are divergent, but our T surface is nice. So if I'm down to 3D again, it's a little even simpler, because I just have some interval on my 2D CFTs equal time slice state boundary and some minimal length geodesic connecting that. So that's the arena that we're in. Now, let's be a little bit careful about taking the flat limit of that. So when I'm in flat space, minimal surfaces are going to have restricted ends. And I think the easiest way to see this is in 3D, where I'm just talking about geodesics. And if I, well, I guess I could, for the case of, if I have a line, then it basically, both of the endpoints are, the line is in the same direction. And so what you'll see is if you just try to like plot in some conformal compactification or equal like time slice, your lines, you're going to always end up at like pi/2 separation. And the angle at which it kind of comes out in your plot will be replacing the impact parameter that you know is that extra degree of freedom of that line. If I had lifted that up to AdS, I would be thinking about shooting nearly, I guess, antipodal geodesics through my equal time slice, but the boundary would resolve that a bit. So That's one funny thing.
I didn't get this, Sabrina. Sorry. If you just had a circle in flat space, so you're in 3D, so the spatial boundary is a circle. I choose any 2 points on the circle, I can connect them with a straight line. Wouldn't that be minimal surface for that division?
So I think the claim that I want to make is that, like, I don't think that you can just take any points on spatial infinity and connect them with a minimal surface. I want to be careful that I don't say something too strong, but I'm saying, like, for example, like a line, like any line through my flat space time, the two ends are going to be pointing in opposite directions. So what it seems like is that basically, like, ends of minimal surfaces, even in higher D, like the set of free data, if I try to solve for the minimal surface equations, it's going to be the thing that would normally be the free data, like the leading shape, is now restricted to being I guess a great circle in the higher D case, and then it's the kind of the angle or the next subleading in our data that is the free data for that, solving for the variational principle for that surface.
But it seems to me that you're restricting to lines that come near to the origin, stay a finite distance from the origin. If I just think of it more geometrically, I have a circle. I can choose any 2 points, and there's a straight line between them, no matter how far those 2 points are. So what's the reason for the restriction?
Yeah. So what I'm saying is, imagine if I take my space-time and I draw take a circle, that circle is now in the bulk, and I draw the line between those 2 points, and I ask where they go out outside of that circle. And I'm saying that formally, at least if I think about the conformal compactification, they're going to end up at antipodal points. So as soon as I put a cutoff, I'm fine. Yeah.
But it seems to me that you're putting, as you said, I think you're restricting to lines that pass within a finite distance of some marked point, namely the origin. If you take a circle and you allow the line, take the radius of the circle to be r, and you allow the line to pass r/2 away from the origin, and then take r to infinity, you can just get anything.
But I still think they end up circling back here. I guess it's a question of
well, let's take r/2. Let's take a 45-degree, a circle that's like this, and then it connects pi/4 and 3π/4.
Yeah.
And then take r to infinity.
Yes. I'm saying that I think that line it'll still basically hug spatial infinity. If I try to plot it on a Penrose diagram, I'm pretty sure that you're still going to end up circling back, because there's still a larger. I mean, I agree that there's an order of limits thing there, but I'm pretty sure I would say that it kicks back.
So sorry, I'm also not able to understand. So if you in this limiting procedure, if you take the 2 points which subtend angle pi/2, right, on the circle, and you take this large limit of large radius, they will continue to subtend that angle at the origin, right? The endpoints.
I can take an order of limits where I decide to always, for every change in my cutoff surface, I can fix the angle. I agree with you on that. And that's picking different geodesics then each time, right?
Yeah. So let's take a limit in which the angle remains 45, pi/2.
Sure.
As it goes. So then this I0 is a top view, right? On the left, there's a top view. Yeah. So in the top view, you will have 2 boundary points which are pi/2 separated.
Yeah.
And in that case, how would the line connecting them look like?
So my impression would be that I would draw a little circle here, and then I would keep it a fixed angle here. And so then I'll be looking at curves that go closer and closer to this circle, which is supposed to be out at spatial infinity.
Even if the points are 45 degrees, you are saying it will just hug the infinity. It will hug the infinity.
I think it will, yeah. Yeah.
But I mean, this is I say, I mean, would it not look like always like a chord diagram? I mean, would it not be like a chord always?
Yeah, straight line.
It'll be a straight line, but I'm conformally compactifying, so things are screwy here, right? It's a straight line if I was looking in.
Okay, so you've got some diagram which makes it look funny, but we know what it would be, right? I mean, what I'm saying is it would connect any 2 boundary points.
No, it doesn't. That's the thing. No, it connects any 2 cutoff boundary points. It doesn't connect any 2 actual conformal boundary points, right?
Okay.
So yeah. So luckily, most of what I say won't rely on that being true.
Okay, great.
But for example, now let's go to null infinity. So if you want to tell me, let me take a larger cutoff near null infinity, and then I want to do the same thing you just described, which is draw the line that goes through those points. It's a space-like line. It's going to go back to spatial infinity, and I claim it antipodal points. If you want a geodesic to end at null infinity, it needs to be null. So that's, I don't know if you believe, would you believe that statement, or you think that you can take a funny order?
I mean, taking this Penrose diagram really seriously sounds a bit extremist to me, right? If we take up, if we put a cutoff as large as you want, we can deal with that and then take all limits.
No, sure. So I think I totally agree with you that the thing I would say in the end is we want to always have some sort of screen, and then you can worry about how things behave on that screen or not, especially from the point of view of, say, space like geodesics and that here. But if you wanted to kind of, if you thought that you wanted a theory like really living on null infinity, then I think you would want to run into the tension of anchoring to a region on null infinity, not a region on the screen that's approaching it. Possibly for the same reason that in AdS, like why people make a hoopla about like specifying where the surface ends rather than where the surface ends on some cutoff really close. When you're in AdS and you're very close to the boundary, it doesn't really matter at all because the corrections to that are like also of order epsilon or order the cutoff, so it's fine. But if I try to lift this story up to AdS, is the picture that I really needed to flow all the way near the bulk point in order for it to be like a finite radius cutoff surface in flat space rather than an AdS scale cutoff surface. Or can I imagine that there's some theory that's living on the conformal boundary where I could do all of the gains? And so the one thing about the spatial geodesics is I think the right way to handle it probably is just put a screen somewhere. And then you can talk about regions of screen and you're fine. But it is kind of cute that like when you think like when someone told you like it's not about the cutoff surface, it's about the boundary, and then you do it in flat, you're like, no. So spatial stuff aside, the funny thing about this null infinity case is, again, if I want these geodesics to make it out to null infinity, and I'm thinking of my theory as living in null infinity, I start to think that I want some like null geodesics coming in, but oh, look, I can't actually tie 2 points in null infinity together with a single geodesic, right? So unlike in the AdS case, where I could be drawing an RT surface between any 2 points in that little time band. So that's one thing that's a little bit wonky. Cutoffs deal with it just fine. But so these proposals are supposedly going to be entanglement entropies for intervals on null infinity. And basically, if I put a cutoff surface, I might be scared that I end up with a kind of a very different geodesic than the ones that would end on that interval at null infinity, for example. Okay. Another thing,
I'm sorry, Sabrina, I'm going to say it in the following way. I'm going to say that you put when you put your you've got a marked point in your space-time, which I'm calling the origin, and a certain region around that, let's say 1 million light years, a radius, and I'm going to demand that everything goes through that region, and then then you can take your cutoffs, and then I think I'll get all the same results that you get. Is that right?
Sure. No, I think that's fair, and I think that the thing that I would say is like you could even if you were doing the AdS story and you just were looking at like geodesics and AdS, like if you're demanding that you're within some region that's like sub AdS scale, then all of those geodesics are going to basically go through that space-time and hit, the boundary in a region that's really close to being this great circle or whatever you're talking about. So like there's a sense in which it kind of makes sense. But again, that's because you're saying finite impact parameter in AdS. And it's just a kind of cute thing that formally speaking, the kind of the free data swaps around a little bit in the flat limit.
Sounds good.
Yeah. Okay, good. But the thing that's going to matter us for more is this null infinity story. And I think it is good to be wary of this proposal is going to have different segments to the RT surface. And why I'm pointing out right now is that I think that part of the motivation when people were proposing it is, again, because if I wanted to formally have some surface that's homologous to that interval, I end up having these segments that are null and going out to null infinity. So I think that's the origin of, at least that why the proposal crossed some cross checks, but we're going to have fun with it. The other thing that I guess is coming here is, right, as soon as I want to try to treat things very similar to like I would in AdS, the easiest thing to do is to put some screen. And then I'm basically putting a cutoff scale there. And I could be slightly worried about like where that cutoff scale is if I'm trying to take a problem of AdS CFT, like that cutoff scale is kind of arbitrary, it needs to be sub AdS scale compared to whatever the AdS cutoff scale is. So I could be worried about how I regulate these minimal surfaces, whether it's universal or things like that. And I think that that's kind of the origin of issues with like defining a finite central charge, at least in like 4D with always 0 or infinity in the celestial story. And I think here, there's some dimensionality issues of the central charges that appear in 3D, but let me just sweep that under the rug a little bit. In 3D, there is a proposal for this holographic entanglement entropy. This is a swing proposal I'm going to get to now. So first thing is 3D is nice because we have Virasoro symmetry going down to BMS3. And so the next slide where I have like little points where there's going to be confusions, which is, yes, it's not that hard to take this algebra and create the combinations that give you BMS3. The confusing thing is that there are different combinations you could take. The one I've drawn here is the one that is the Birolian combination. And there's the automorphism that would basically flip like this bar ln to like negative of negative this guy. So negative L of negative n, and for the central charge sign out would be a Galilean contraction. And so this is the combination that we want when we go from the cylinder down to flat. And because you have this mixed modding of like left movers with positive n and right movers with negative n in the same rotations and translations, when people have computed things in BMS field theories, they have results that look weird, and it's coming from that. So basically, algebra makes sense, fine. But once we talk about which representations are natural, I think that's where the rub is, or where some things look funny. So basically, by demanding that these twist operators would be primaries, like BMS field theory primaries, which for them are basically annihilated by the ln that are positive and the mn that are positive, they propose the following entanglement entropy. And note that if we take this limit here and we had just normal Einstein gravity, the like left and right central charges are the same. We would have CL being 0 and CM being, I guess it's like G over, sorry, like 3G, like G over 3 or something. So basically what happens is that this term is 0 and you end up with the term, which is just the second term here, which is LU cotangent of L phi over 2. So we're gonna unpack why that looks a bit weird, but basically it would be saying that they want to claim that if the interval has 0 height in some sense, then you'd have 0 entanglement entropy. And also they don't get an absolute value in this computation, which we are going to point out kind of where it tracks from. And so kind of red flags coming up there. It's not like obeying, I guess, strong subadditivity. It looks funny when you try to like combine intervals near each other to extend them. And it's all coming from by like the choice of demanding that these primaries are going to be primaries of this BMS3 algebra that are BMS primaries, so highest weight with respect to these ln and mn, which are these funny combinations of the Virasoro. So sorry, that's a bit weird.
Sorry, the result for this entanglement entropy is a field theory result? Is a result worded in the language of field theory?
Yeah, it's so what they do, and they're basically Galilean people, I guess. So it's like Grumeller and Riegler and Bagchi. And so the steps that they show, they are roughly co-opting a Galilean result and then flipping some central charges in the end. But they claim to also check it with some like Wilson lines. It's a Rennie entropy computation that is just using like I'm trying to think like the steps. The main step is where they create these combinations of like the flat limits of the stress tensor, and I think they swap out like a normal, like the normal computation you have in like Carty's book, but then like later they flip the central charges out as like kind of a trick. But they claim that it's a BMS field theory computation.
And is there an example of a BMS field theory where one could check this independently?
I mean, there are definitely examples of people studying BMS field theories, but I'm not sure that they're that they can. I don't want to claim that I would know how to like find the papers where there's some free theory and then, but yeah. So there are tricks that they did there. They made a claim. And then what happened is that Weisong and friends found a bulk quantity that equaled that claim. So it already makes it more interesting. Whether or not you want to say that's a good entanglement entropy, they can be this thing, and there's a bulk quantity that ends up being equal to that thing. And what it ends up being is it's the minimal length, or the absolute value of this guy, is the minimal length geodesic that happens to be between two radial null geodesics. So that length of that space-like thing equals this quantity. And then they try to say it in a more covariant way, but we're all going to have little red flags popping up. So the swing proposal was that this BMS field theory.
What is the? Can you again say what is the geometric quantity that matches this number?
Yeah. So I take I draw like an interval on null infinity that is roughly like supposed to be some slice of null infinity. So like maybe not an equal U cut, but some cut there. So I try to draw this line in blue. Then I shoot out like the radial null geodesics from that was 2 endpoints. And I look at the minimal length spatial geodesic between those two.
Shoot these geodesics out to where? To the origin?
So from the two intervals at null infinity, I shoot the radial guys inward.
Okay.
So even though like they will go through it's radial, right? That doesn't mean that the like minimal length geodesic between them is 0, right? Because they can be different times. But that is why it would be 0 if LU is 0.
Yeah, but this also makes sorry, it also makes clear that you're really choosing a particular point is really important. Choosing it
right when you say radial, right? Like radial is a red flag, modular flow red flag, and so like these, but so like they make this claim and they spruce it up a little bit.
One more question.
Just
because I didn't understand. So this, when you draw the geodesic, there is what are the endpoints? I mean, it looks like from your picture, endpoints are chosen somehow, but I could choose one point there, and the point on the other guy could be somewhere else.
Yeah, I think minimize. So what I'm so this little swing here is the minimal length one. Yeah, you slide it around, and you're trying to find the minimal length space-like geodesic between these two rays.
But I would imagine at the origin they would just come together, giving you 0.
No, that's you would be right if LU is 0. So if you literally took
LU,
equal
U, yeah. I didn't realize there is an LU.
Exactly, but you're totally right. If LU is 0, because I'm on a U equals 0 slice, for example, then it's 0.
But then LU is 0. I should get the first answer, right? First term as the answer, not 0.
So LU, yeah, but sorry. So this is in Einstein gravity. The first term here, CL, is central charge left mover minus right mover, and that's 0. So this term is vanishing by nature of the bulk theory. Okay. And then
I see. Thank you.
Sorry, if we vary over all endpoints, do 2 points sometimes become time-like separated?
They do. And so, I mean, sorry, do they? Sorry, actually, I want to be careful before I said that.
Or does it tend to null at infinity?
So for example, like, I mean, these 2 points are like the 2 ends of the rays are going to be null separated, obviously. But like I'm saying that they're in some sense they're antipodal on this diagram. So I'm trying to remember if maybe I can whether I would draw this diagram and think that this point and this one are time-like separated. I think they are time-like separated, but
so sorry, I was going to ask that if there is a place where the 2 points are time-like separated, that at some point they become null separated, and so you should not really say minimize, you're saying extremize.
Let me be careful. Yeah, I'm going to double check before I say that they're time-like. I think on the boundary, what I was looking at was, sorry, I'm just remember drawing myself because it's been a little. So these 2 are null, and then. There's a part of me that thinks there isn't another saddle. So like there's a reason later where I'm actually I need it's like need more coffee or something like that before I claim one or the other. But I know that there was an extremal sort of the space like, and I am tempted to think that they are not. What am I going to say? I just needed pen and paper, and to in the bulk I would want to just pick a symmetric interval where like you're sitting at like LU here and here, and then yeah, I'm a little bit worried that they might go time like, but I'm blanking a little bit there. It's easy to check. Yeah, sorry. Yeah.
If you take any point on one of these lines and shoot a light cone
I think they'd be time. Yeah, they should be time like, yeah.
No, I was just saying that even for space-like guys, probably. Oh, I see. Probably not for space-like, but
it's just like, is this one and this one time like separated? And they look like they are in the figure, but I just don't want to be.
Yeah. But when we look at if we're counting space-like distance as positive, then what you're trying to do is to maximize the space-like distance between the two points.
Minimize.
This I cannot understand, because if 2 points are more or less light-like separated, there's a minimum which is 0.
Oh, no, so that's where I don't want to claim that they're like, I want to be careful before I say that these two.
Okay. Yeah. Thank you.
Yeah. Sorry. No, I mean, there are two null arrays, and the minimal length space-like geodesic is the quantity that's equal to the absolute value of this guy. That's a true statement. And then it should be easy enough. Like at the end of the talk, we can do the pen and paper just to check where they end up being like if they do.
No, I'm sorry to disrupt, but
no. Yeah.
I just wanted to be sure that by minimize, I was getting the sign right. Are you counting space-like distance as positive when you say minimize, or time-like distance as positive when you say minimize?
So space-like should be positive, and this is the minimum length space-like geodesic. Okay. I know that's a true statement for sure. I agree with you. I'm bothering myself about there was a time when I probably computed something close enough to this where I'm like bothered that I can't answer that. So we'll come back to some figures and we can maybe think about it later once we're there. Good. So the claim is that this minimal length surface between these radial guys, which ends up being this quantity that's the bench is equal to this proposed entanglement entropy by Bagchi and friends. So they have this quantity that's equal, and they try to frame it in a slightly less like background, I guess, like they want it to be true beyond being in, say, flat space by saying approximate modular flow. But kind of the thing is that their trick works. They can use this like Cassini-Huerta-Myers type story for these like space-like modular flows to match their answer. So they're mapping to some like inner BTZ horizon with the CHM trick. But again, that's like still only like using that trick is only valid in certain nice background spacetimes. And so there's a lot of red flags here. The fact that you're picking radial null geodesics already is weird. And then the fact that you would have this approximate modular flow is a red flag. But it is cute. Someone found a quantity that's equal to this other proposal, and then they're playing with it.
But in the AdS context?
Wait, understand. No, just to I mean, this in this Bagchi and Friends' proposal there. I got a feeling that you're working in 2 dimension where the thing was Virasoro, the algebra was Virasoro times Virasoro, and some contraction was done to get to this BMS3, right? So what is LU there? I thought the 2-dimensional boundary, code boundary was carved out by some equal time surface, which would have same LU everywhere. So when we say LU or when they say LU, what exactly they meant?
So I have a 3D book and I have a 2D boundary, and in that 2D boundary, I have my U coordinate and I have my phi coordinate. And so I think a lot of the things that they present, or at least the one I'm interested in is when it's really a cylinder. So U is still time-like, and I can have a delta LU there. So it's like an interval that's tilted.
Okay, thank you.
Sorry, phi, you just have U and V on boundary.
So it's not an equal. It's not going to be equal U. It's like you have 2 points that are the endpoints of the interval in the U and phi plane.
Yes.
Sorry, one quick question. In the AdS context, the RT formula we understand from sort of this Lukowitz-Maldacena type argument, right? Like by using bulk replica symmetry. Does this prescription follow from that kind of an argument, or has there been an attempt to?
I mean, I would bet it shouldn't from the so I think that there might be claims in some of these papers that it could be consistent because it's a fixed point of the modular flow, but I do not think it should in the end because I don't think it's going to be an entanglement entropy, right? So,
okay.
But then I'm going to raise some questions about whether or not you want to say that the original like RT proposal makes sense in the bulk point configuration flat limit. So I think there's still fun questions related to the fact that this quantity is in the flat space, like center of AdS, versus the original RT formula. The RT surface is hanging out way away from wherever this flat scattering point is happening. So it raises an interesting tension no matter what. So now that we have this quantity, we can ask all. Yeah. Oh yeah.
If it's not too disruptive, could you please explain what the geodesic being tangent to the modular flow means?
Sure. Okay. So sorry, I'm gonna make sure I understand. Can you repeat the question again, just because I might have misheard the.
So the quantity it's supposed to be equal to is the minimal length space-like geodesic between radial non-geodesic tangent to modular flow. So what does the last part of the statement mean?
I think I'm missing the end of your question.
I think the question is what does it mean that it's tangent to the appropriate modular?
Yeah, sure. I think that's kind of bullshit. But sorry. So the thing that's true is if you look at just the modular flow is basically going to go along like some Rindler horizons coming back from these surfaces, and it happens that the null geodesics are literally tangent to that flow, but so is any other like the choice of radial, I don't think is actually isolated by that claim. I think the choice of radial is still magic sauce, right? And it's not really well explained or thought out, but like it does give you the right answer to this quantity they wanted. So that's a red flag. But they literally, like if you literally were plotting, like say on the boundary, I pick points and I find the vector fields that stabilize those points, then like in the bulk, those vector fields extend and like all of these surfaces are tangent to it. It's a true statement. And they try to define it that way. But so is any other null geodesic coming from that point, I think.
Yeah, I was just asking what modular flow means in classification. Like, is it just regular flows?
So it's almost like it's just straight up which Poincare transformation preserves those two endpoints.
Okay.
Yeah. Great. Awesome. So now all of this discussion can be lifted up to AdS. I mean, as far as the geometric quantities can, and the proposed interval that you're looking at can also be lifted to this bulk point configuration. And so you can try to say, what the hell are they doing? If I lift things to AdS, can I make sense of these quantities? Can I find some information theoretic interpretation of the bench? Can I try to see why they might be guided towards like the swing proposal as opposed to like the normal RT proposal? What gives? So one thing that I think is slightly funny is if I tried to, and this I'm happy to, it's a very talkative file, which is awesome. So we can it's fun to play with things, especially when there's no paper out. So like, let me try to raise the question I'd be confused with, which is I have this bulk point configuration, and I'm very happy that I have this tiny region in the center of AdS where my flat space physics of scattering is going to happen. And I also have a window on the boundary where I wanted to have my boundary theory, like the operators that are going to cause the scattering living. If I took an interval on that boundary AdS, whether it's equal time or not, it doesn't matter. I find this RT surface there, and it's this black line or whatever that's going through AdS, but very far away from my flat space region. And so with the luxury of this AdS box, I have a holographic RT proposal for this interval in the field theory. And that RT surface, first of all, has a length that's going to be like large, like AdS scale size, and it's going to be way far away from this flat limit place. So there's certainly something funny that like I don't have an analog of this quantity in flat space. Maybe I do once I put a cutoff, and that could be the resolution is like just put cutoffs everywhere, then you have space like geodesics in that cutoff and we're fine. But it's not sitting in the same place. The kind of fun thing is that this swing proposal, because all of my geodesics are basically tuned to be very close to plus or minus pi/2, will still go through my my AdS in a region that's sub AdS scale, right? So they're going to come close to each other, and like the minimal length space like geodesic will be the same swing bench proposal because that didn't change when I extended those geodesics out to my boundary. And so that swing is still there in AdS, and it has the same funny definition in terms of this bulk point configuration, but it's clearly not the RT surface. So it wouldn't be the entanglement entropy, at least if it was the normal CFT sitting here, of that interval. So,
sorry, by the way, a quick comment.
Yeah.
Here it's totally clear that at least in the AdS setting, that the points go time-like separated.
Good. Yes. And I definitely want to play with that more for a reason that I'll come
Sure. I didn't want to.
Oh, no, I'm happy.
As a comment.
No, this is good. I feel like my brain's not working when I'm like asking, like it's a good question. And I feel like I should know, like, okay.
Yeah.
So yeah, good. Perfect. So there's going to be an issue there. And I would like that to come in, I think, but I don't know for sure because of it just, there's a way I want to tie a story of it together that I haven't figured out yet. So we can go back to it. And so first tension is, this is not the RT surface, this is just a bench sitting there. So that's bad. The obvious red flags are proposal doesn't match what we expect in AdS. This BMS field theory entanglement entropy is 0 for an equal U cut. What the hell? Again, not like what we'd expect in AdS. It's not even positive. Yeah.
I don't quite understand this proposal does not match with what we expect in AdS, because there the question is different. Here the question, I'm not sure what it is, but it's probably not the same as the one that we ask in AdS.
Exactly. So if you ask the same question in AdS, it's not the same answer. So maybe let's say that's a red flag.
No, but
and so if you
same question, right? I don't quite understand in the flat space what kind of question is being asked.
You want a field theory living in null infinity, who you can compute
but that's not the same as
entropy.
the standard 2D CFT that we talk about.
Exactly, but supposedly that. So you can ask maybe what's going to get around it. So that's why I don't want to kill like their discussion just off the bat because it doesn't match AdS. But if you wanted to like, if you might say like a vacuum entanglement entropy for this, like a theory living in null infinity, if it's supposed to match from like map from this bulk point configuration, you might have thought that they could have the same entanglement entropy. Or at least it wouldn't be obvious to me that they shouldn't be. Right. But null infinity is weird, and I agree boundary conditions are weird. So I'm not saying you're going to throw everything away, but it's not obvious to me at all that they would have to be different for sure for vacuum entanglement reasoning.
Okay.
Yeah. So now I think the bigger red flag is whether that quantity even behaves like entanglement entropy. Like if I try to like extend my interval a bit, the fact that like if LU is 0, it's 0, things like that seem finicky. I think you would probably find some entropy inequalities that it doesn't obey. And then radial geodesics from the bulk perspective do not sound special at all, and they surely shouldn't be. So all of these things are red flags. And so maybe like, why am I even considering this in the first place? Yeah. But the kind of fun thing is that you can still ask, okay, so they came across it. There's a quantity that lives in flat that is equal to this twist operator computation you can do in this BMS field theory. If you assume certain highest weight reps, maybe it's interesting. Maybe I can lift that story a little bit up to AdS. And so one kind of fun thing is that there's some nice information theoretic quantities that a colleague of mine, Alex May, has been studying in AdS CFT. And a lot of the papers, I think, are focused on, say, 3D bulk, 2D boundary. And there he has a claim that, or he has a proof with Pennington and Source, that when you have a bulk scattering point, there are certain regions in the boundary that have to be have a connected entanglement wedge. And so the existence of a scattering point gives you a connected wedge theorem for him. And so the more cool thing about what he did is he was very motivated by a QI side of things. So rather than, I guess, like Malvicena or friends talking about singularities that can occur in the CFT versus in a perturbative field theory in the bulk, he's just doing quantum circuits and the fact that different pairs of points have light cones that intersect. That causality is letting him have certain protocols where they can communicate with each other, and then the entanglement is the resource for that. So from that motivation, he would say that, okay, I need to have entanglement in order to reproduce bulk scattering in the dual, and then Pennington and him have a proof. Now, the cute thing that happens is that the form of this proof is just a bunch of like focusing.
If you don't mind, could you just make the statement? I remember looking at that paper long ago, but I've forgotten it.
Yeah.
So what was the statement that if 2 points from the boundary can go meet in the bulk and scatter, then something, what was that something?
Yes. So the something is the following. So if I think about the kind of 4 points that are scattering, so these are the same, like R1 and R2, C1 and C2, in the book, I asked for them to be able to literally like have I guess the future light cones of C1 and C2 intersect with the past light cones of R1 and R2. So there's a bulk
they meet, collide, and
yeah. And then on the boundary, I track their light cones. And so what I'm doing is I'm creating these two regions, R1 and R2, which are, say, future of C1 intersected with both the past of R1 and R2. And then same thing with C2. And so those two guys are going to have a connected entanglement wedge if there is this bulk point here. And then the structure of the proof is some focusing arguments where you're taking like candidate RT surfaces. You're asking whether if it's connected, then it's like the minimal surface is the one here versus if it's disconnected, then the two here are minimal. And so it's a bunch of kind of comparing, I guess, like focused minimal surfaces. Yeah. So that's the structure of the proof. And the claim is coming from this entanglement needing to mediate this protocol. So that's kind of cute. Now, it turns out that if I engineer a very forward scattering configuration, then I can put myself in a situation where that swing bench is equal to a mutual information. And like the kind of easy trick to see this, or the easier way to see it, is that there's a lower bound for Alex's proof that if I was in global AdS would just be saturated. And so I can engineer a global AdS scattering configuration for which I haven't computed an entanglement entropy, I've computed a mutual information. And so maybe the one kind of cute thing that's come across is that as much as like this entanglement like wedge RT surfaces are very much outside of this scattering point, this kind of you're probing physics in the bulk point with this like swing and with the ridge that he would use in his proof, even if that ridge is not itself the information theoretic quantity, it's just a lower bound. So
Sabrina,
swing,
sorry, just to make sure I'm sorry, it's really late at night for you.
Oh, no.
Sorry for delaying so much.
No.
Okay, but so the point of this paper was that while the causal light cones of the two of the boundary point, the causal light cones may not overlap, the entanglement wedges would have to if these causal things overlap in the bulk.
In the bulk.
Right?
In the bulk. Exactly. Yeah. Okay, so you can never 4-point scatter in the boundary, but you can in the bulk. And yeah.
Okay, thank you.
Yeah. So that's a cool proof. And then the cute thing about, or at least how I entered the project, was just the kind of simple or cute observation that this component of the proof end up being equal to the swing bench if I chose a nice kind of configuration of intervals. And so that's neat. And that's why it's equal instead of a lower bound in that global AdS context. But you can already see that it's not an entanglement entropy, it's a mutual information in that context. So that's a true statement that in global AdS for the single interval case. And then you can ask like why that ended up being true. And maybe I should have put more equations to it, but roughly what it amounts to is like you're taking the difference of left movers and right movers. And that comes from the fact that the flipping between the ultra-relativistic and non-relativistic limit in these Galilean field theories versus Crowleyan field theories ends up swapping that central charge out. And so the mutual information in global AdS for that single interval is actually like left entropy minus right entropy, which then is equal to this BMS field theory quantity because that computation tracks through doing that kind of automorphism. So that's kind of the explanation for how in the global AdS case, they landed on this mutual information in AdS, or sorry, in global AdS, the uplift of this term. So yeah, so that's cute. But then, so basically you could pause here and say, well, what did I do? I dug up some computations literature that were self-consistent with each other, and then I half-assedly explained them and then half-assedly try to say, maybe they're not interesting, which is not good. But the kind of funny thing is something actually, so this is especially on the margin, some things seem to work more than that. So basically, the kind of funny thing is Hijano has these papers where after he was going through, I guess, like geodetic Witten diagrams and semi-classical AdS blocks, him and collaborators went over to the flat space story. And I guess they were also aware of these proposals by Wei Song and friends. And they were able to reproduce BMS field theory correlators from some geodesic networks.
Sorry,
Yeah.
to take it back to the last slide.
Yeah.
What is what you're saying is that when they go from the non-relativistic to the ultra-relativistic limit, if they swap out the central charges. So are you saying but the quantity that Bakchi and Friends computed was the entire, I mean, at least that conjecture was that it was the entanglement entropy, right? Not the mutual information.
Yeah, so they were intending to compute an entanglement entropy for twist operators that were highest weight reps in their like relativistic limit that ends up being this flipped thing compared to the usual reps I'd be doing in AdS CFT. So you can track the fact that they get kind of this like LU cotangent instead of a I guess the first looking term, precisely because of this sign flip in the central charge. So when I was saying CL is 0, it's because Einstein gravity in the book would have left and right central charges equal. And so it's like almost like you had an auxiliary bulk theory that had like them flipped, like a very chiral theory.
But what was your point? You were saying that what you were computing in the global AdS context, like the quantity dual to it was supposed to be the mutual information?
So yeah, so the BMS field theory people would have claimed that they computed a Carolian entanglement entropy, but they secretly computed it by, I guess, assuming the twist operators were in reps that I wouldn't have assumed if I'm trying to say that I put twist operators, say, near the tau equals pi over 2 like points in my AdS CFT. So I think that their whole sign flip that gives you the mutual information as opposed to the entanglement entropy tracks to that assumption about the representations of those twist operators.
I'm just confused because the relation between their computation and your computation isn't affected by this, right?
So I would say if I flip the value of the central charge out, I would flip like the term that would be CL would be non-zero and the term that CM would now be 0. And so if I were in AdS and I was putting twist operators near like some values of U and phi, and I computed those, I guess, like use the twist operator correlators to compute some rho to the n, I should get the usual RT proposal. But if I had somehow flipped the value of the central charge, I'd get their quantity. So it's like I can shuffle it around. I think the claim that I want to make is that they're making a different assumption about the twist operator highest weight states.
Okay, I think I'll ask you later.
Yeah.
Sorry, Sabrina, just maybe I can ask in some different way, perhaps in some context.
Yeah.
So the LU vanishing, this quantity still vanishes, right? When the LU vanishes.
Yeah.
So now that you have some understanding, what does this mean? Is this expected that for LU this quantity vanish?
I guess I could try to ask if I would have to track what I guess it would have to mean that like the left entropy is equal to the right entropy, so maybe it's a very symmetric interval or something. I haven't thought about the phrase that way, but
because it's a mutual information. Is that the case? There's supposed to be a mutual information now?
So it's a mutual information in global AdS, and I don't want to say that's more generally. And there basically, if LU were 0, I'd just be putting my operators on these 2 dashed lines, and then be asking about the I guess like the left movers and the right moving distance or something might be the same, and that's the origin of what's happening there. I'm gonna have to be a little bit careful if I say that, but
okay, thank you.
Yeah, I think it should be true. So yeah. So basically before this slide, I would say everything looks like, why were they looking at that quantity? Maybe there is something funny about flipping some weights in the BMS field theory computation, and it's cute that there's a bulk like thing it's equal to, but whether it's a cute trick that I can identify as mutual information, I could just say that there's some confusion in literature and that's not necessarily as valuable. But I think one thing kind of cute is that these null geodesic networks really do compute BMS field theory correlators. So correlators that behave like they are primaries in the BMS field theory, at least in the global for sure. And be a little bit careful. There's some claims about like technically, I think he talks about BMS blocks and not just the Poincare blocks. And I haven't fully digested that enough. But the first statement is, these things are working more than you might expect. If I smear a bulk operator along a radial null geodesic, why are their correlators matching BMS primary correlators? So one should take that question seriously. And then if you do, you kind of have this fun thing that I think hopefully will actually like get through more computations with it, but at least at the level of just putting the single particle operator smeared along a bulk geodesic, the kind of cute thing that you find is that, like, if you follow an analog of the Hiroshi and Oguri Nakayama paper when they were rederiving like HKLL from a symmetry perspective, you can say, if I put a light ray operator, like a light ray in the bulk, so it goes between two antipodal points, there's the impact parameter here. And I ask, what representation does that operator transform in? I'll find that it will be highest weight. And I can check what the like conformal dimension would be from the point of view of a conformal frame of like operators sitting here. And I find that it's basically, for the 3D case, a linear combination of the two light ray operators, it seems. So I'm basically using the mass shell condition to check that the spin is like 1 minus delta or whatever. And then delta is, I guess, 1. And so what's kind of cute is then it asks the question of whether or not there is a sense in which I might be interested in looking at correlators of either like light ray operators that go between antipodal points on the AdS boundary to try to spoof these BMS field theory computations. And one cute thing is, if I basically have a very highly spinning particle and I take the flat limit, I get the form of the correlators that they're interested in with the weight there. Like, so I can take a massive field and smear it along a bulk light ray through the bulk and produce a primary living at null infinity in this BMS field theory. And then you can ask, well, technically speaking, if all of your funny, like dealing with 2-point functions of light ray operators is already tricky, because normally you say that now it's a vacuum, but you have to be careful that they're not they're not time, like they're not acting in the vacuum. I think there's some subtlety there that has come into play. You could ask, like, maybe there should be terms from both of the two different light ray directions. And that would make me think that I shouldn't just get this like absolute value swing guy. I should get something from the time like separation, like you're saying, or I mean, I don't know exactly the origin of it, but basically I want to be able to reconcile those observations. And I think that's where the kind of fun business is, and this is why it's very much work in progress, is that there's a claim that if I'm in AdS, I should have it be equal to a mutual information, which I could be able to place these twist operators at this kind of zigzag separation. But at the same time, there's the claim that this null geodesic network in the bulk would produce it. And so I can basically try to decompose those guys in terms of light ray operators in the boundary from the representation theory point of view and try to see how that story all matches together. And so that's what we're playing with. But I'm not sure how far we'll go, or if we can find a better way to frame some of the earlier things and chop that off. So I'm having fun with that, because light ray operator it went more into CFT stuff than I thought it would.
So the operators you're smearing on the light ray, which theory do they come from?
So I don't want to say that I can just light ray transform twist operators, because I like shifting things by order 1, especially when you want to take n to 1 in the end. It's not clear to me that I can treat things as so heavy that I can drop like this order, like this one shift and keep it. But it almost looks like I could light transform the twist operators in the normal CFT and compute their twist operators. But I don't want to, I have to be very careful that I'm saying statements about the global algebra here when I want to make this claim. So,
yeah, pictures look like they're in the light rays in the bulk. Am I missing something?
Oh, sorry. I think you're not, the Hajano's paper works because you end up, like, even though he didn't phrase it this way, you can check that if I put a light ray operator that's on shell in the bulk and smear it along a light ray, that it should transform in some superposition of the CFT light ray operators that go between those points. I think that's a true statement. Like, I have notes that derive it, and then there's probably some caveats about uniqueness of I don't like, yeah, definitely want like not say I've proven that, but it's neat. I don't, yeah. Say again?
You're saying the quantum numbers match?
The quantum numbers match. Like I checked the high speed condition. I checked like the delta and then absolute value of J, and then I had some argument for the like the directions of the spin, and at least in the 3D case, it's easier because you just have 2 points, and so basically the translation in the say the x2 direction is just changing the superposition of the 2 light ray operators. So,
and you're saying the correlators of these so these are CFT light ray operators, and you're saying the functions maps the VMS.
That would be the check. So the claim is that the bulk computation, if I use like in the flat limit, you can just do the propagator between 2 light rays and you reproduce the swing bench. And then if that's true, then and it was also true from the symmetries that each of those guys should be dual to the CFT quantity. You should be able to track some prescription where it matches in the CFT side. Now I need to do that, but like at least it's kind of fun to have things that like if it needs to be like, yeah. So yeah. So I guess I never had thought until reading through Hijano's papers and in hindsight a little bit that one way I might want to talk about primaries living at null infinity that are massive is this kind of like bulk operator that's massive smeared through the bulk, which would somehow be like these like light ray operators around spatial infinity. So it changed my perspective a little bit. And I don't, but we'll see. So that's basically what I wanted to talk about. And so I'd say the 3 next steps are basically revisiting and maybe helping discuss more with like Rob and Jackie how to frame the question instead of just being like, oh, these people propose this thing. Oh, I'm confused by it. What the right entanglement entropy I really should think about for an interval in null infinity, or where the subtleties really lie. Is there a role for these swing surfaces in AdS CFT, or like can we define quantities that kind of live in the bulk point region that are like the holographic duals of information theoretic quantities in the boundary? And then I think in particular, I'm going to have fun with these light ray operators through the bulk and the flat limit and on the boundary theory to reproduce kind of the highly spinning guys that you assume when you swap like Carolean and Galilean limits, I guess. So that's what I wanted to say. Thank you guys so much for the questions because it's definitely very helpful to the workshop. But so thanks.
Thanks, Sabrina, for a second. Questions? I have a naive question about the VMS CFT.
Yeah.
So you were discussing results in the VMS case, and then you moved to AdS CFT, and I missed the part about the VMS CFT in this picture. So what's the?
Yeah. So maybe the easiest thing is to just stare at the algebra. Maybe. So the limit that I'm taking is this large L limit, which is like the AdS scale. And then I guess some funny business is in like the fact that these combinations are order 1 in that limit.
You're saying the dual CFT, if you take the limit corresponding large AdS radius in the dual theory, it's basically this VMS.
Exactly. And so like strictly speaking, like I'm thinking about living in the cylinder, and I want to have like I'll have like the L0 and L0 bar modes mapped to like positive mass and in the flat geometries. So this is the limit that you want to take for their like when you write the vector fields down on the cylinder. But
Sabrina, very vague question.
Yeah.
If we were looking at light ray operators in a CFT itself, and forgetting for a moment about the connection with holography, one context in which these light ray operators appeared was this Maldacena-Hoffman kind of experiment.
Yeah.
In which the claim was that they were computing the nearest thing you can get to one of the nearest things you can get to an S matrix in the boundary CFT.
But it's different though, right? Yeah. So the thing for them is that I would say that those light ray operators are okay. So in Hoffman-Maldacena, I would say those light ray operators are in a 40 CFT and like they're near null infinity. Now, to be fair, like the configuration of light ray operators I'm looking at now would basically naively look like they kind of are partially along null infinity and then like featured past null infinity. So but they're definitely not in a 40 CFT. So it's not as obvious to me that they're the same motivation as Hofmann-Maldacena.
Yeah.
But I definitely, so the kind of, so the closest thing I've seen to like when I was going through literature to try to derive or like figure out whether it made sense to talk about the bulk operator being dual was something like shockwaves, I think Hartman's paper. And there it's like they were using the Anik operators and some like spherical shock when they were, so like they have a HKL derivation of something very close to what I was trying to just use like the highest weight states and hope that things are unique enough. So I definitely don't want to throw out looking again at Hofmann-Maldacena, but I wouldn't say it's the same context. But
okay, thank you.
Yeah.
So the is the aim to find the quantity which is dual to this the swing surface that you were, I mean the length of the swing surface that we were talking about, or are you convinced that it is one thing or the other? Like, is it maximal entropy? Sorry, is it the mutual information? Or,
so I think I agree that I think that I need to workshop the original aim was just to understand like entanglement entropies in flat space, and that there are like two proposals. One proposal is roughly to put a cutoff surface and talk about just space like geodesics and equal time slices, and the other proposal is the swing proposal. And or maybe there's others where you're talking about viewing null infinity as a Cauchy surface too, but the ones where they're very like holographic, everything's on the boundary. Those are two options. And in the process, I guess I didn't realize how some things were more subtle in flat without a cutoff. And so I thought it's neat, whatever. But that was the original motivation. And I would say that the more interesting thing probably is not in just shoring up like who computed entanglement entropy or not, but more like are these quantities interesting? Like, should we be like talking about I don't know exactly. I think what I want to say is like if I was like I'm tempted to really think that I just want to tie myself to AdS CFT and then ask what information theoretic quantities probe things that are nice in the flat limit, I guess. Like I don't know how to frame that more specific, I guess roughly speaking, is there something that Alex May knows about that really is something about like flat physics as opposed to like where like all the AdS scales go away. So I think that the thing that was driving or at least validating computations that maybe these guys like in Brussels were doing is that like L doesn't appear in the end. Like the flat limits they're taking have some sort of like nicely well-defined guys. And then in the end, this like this bulk thing that Wei Song proposed is again living in flat. So there's something nice about everything living in flat space on the boundary and in the bulk without a cutoff. I'd like to understand those class of things better, but I don't know how to frame it without saying not this. Yeah.
To see if I understand, so you're saying this swing length as you showed, so it's a well-defined quantity in global AdS, and it might be relevant in the bulk point limit, like when points on the boundary are in a regime where the bulk point limit is relevant. And
well, I think
and obviously this should map to something in the boundary CFT. The question is if it survives the transition from boundary CFT in the AdS CFT context to flat space physics as in the bulk point limit.
Yeah, so I think I kind of have a preference for quantities that I can define in the AdS boundary and in the AdS bulk near the bulk point. but I don't always have the freedom to do that. Like I have this accident of the way that this focusing of these RT surfaces when I'm actually in global AdS just has this ridge that's living in that bulk point region. So I don't know if that's that probably is not the right safe way to frame things. It's just something that I thought I liked. But so the main motivation is understanding RT proposals. And then the thing that I wish I understood better is like how much of flat holography can I really do where I have the bulk and the boundary of flat space, and how crucial is the cutoff? I want to appreciate better that aspect of the flat hologram. Maybe Busa would already say Anderson's it, but I definitely don't, and that does sound surprising. So yeah, that's the theme of things. And then I'm personally interested, like, to be fair, like, I think each of these observations, if I could tie it back together, it would be, there would be a computation where I would be able to see, okay, so these, even if I don't say they're the twist operators that I'm like transforming, there's some operators that I would formally be like transforming to reproduce the correlators that they're using to claim that these correlators are a row to the n or whatever, these running entropies. So if that's true, then I should be able to track that through and understand how the mutual information computation came from these correlators of light ray operators. And so that uses more CFT than the individual computation. So I think there's some fun things there that I would learn in the process. And that's just me. Maybe I like like learning things around different questions. But I think that, like, if I try to distill a more not personally interesting question in that last part, maybe, okay, if I went really too far afield, I would love to see how Alex's proof could be proven in the very CFT side of things, to the extent where, like, you're never talking about like bulk point singularities, even though strictly speaking, you are always tracking through geodesics. So maybe that somebody could do that already, but he's framing his answer very differently. He's basically, the mutual information is what be twist operators that are space-like separated in these two intervals, versus the question of there being a bulk point would be asking about singularities when you have 4 points that can scatter in the bulk. So like the mechanics of how Alex would prove that, I think would be using similar ingredients to what I would need to know to be able to prove like that everything checks out and that these bulk light ray geodesic networks were these boundary light ray operators whose correlators were the mutual information. So I'm interested in that space of things, but I still think I need to hone that better question about that last part about what's actually interesting to other people versus like you try to build massive states and you never even thought I could just take a massive operator through the bulk, and because it falls off at null infinity, it's a good thing because that integral converges now. So yeah, sorry, I'm rambling about things that I find like funny that I didn't appreciate I should have, but
given it's midnight for Sabrina, maybe we should thank
you
her
guys
again.
Thank you, Sabrina.
Thank you so much, Sabrina.
Yeah, thank you so much.
Okay.
Awesome.
Bye.
See you guys. Bye.